Good morning. Thank you for coming to our Aeronautics Technical Seminar Series. Today's topic is the recent progress in aircraft noise research. This is a very important research topic in aeronautics, and for those of you who are familiar with NextGen, you're well aware of the goal of that program, which is to enhance the capacity of our system by 2 to 3 times by 2025. And when you think about that challenge, you realize one of the key drivers in being able to design that capability is going to be overcoming environmental constraints. And noise is one of the key drivers in those environmental constraints. So the research that you're going to hear about today is very relevant to today's problem, very relevant to NextGen. And I, for one, am very excited to hear about it. Before we start, I do want to introduce our two speakers. Our first speaker is Dr. Edmund Envia. And until recently, he was the associate principal investigator for the acoustics discipline under our subsonic fixed-wing project. He joined Glenn Research Center in 1997, but he has been involved with a number of NASA engine programs since 1987. His expertise is in theoretical aeroacoustics, and he has been responsible for the development and validation of turbomachinery noise prediction capabilities and fan noise reduction concepts. Dr. Envia received his PhD in 1988 from the University of Arizona in mechanical engineering. He has authored over 30 publications in aeroacoustics-related areas and is an associate fellow of the AIAA. In 2005, he was awarded the NASA Exceptional Service Medal. He has been a member of the editorial board of the International Journal of Aeroacoustics since its inception. Dr. Russ Thomas is our second speaker, and he has been involved in a wide variety of acoustics research with NASA for 17 years in areas including fundamental fan noise research, active fan noise control, advanced acoustic liner concepts, and primarily in the area of propulsion, airframe, aeroacoustic interaction effects. Since joining NASA 8 years ago, he has held researcher and team lead roles. Currently, Dr. Thomas is serving as the Associate Principal Investigator for the Acoustics Discipline under the ARMD Subsonic Fixed-Wing Project. So for those of you guys who are paying attention, Ed was the former API for acoustics, and now Russ is taking over as the API. So we've got a good tag team going on here. He recently completed serving on the AIAA Aeroacoustics Technical Committee, where he was also general chair of the 2006 AIAA CEAS Aeroacoustics Conference. He has co-authored over 30 publications and holds 2 U.S. patents. Dr. Thomas earned his doctorate in aerospace engineering from Virginia Tech in 1987 and spent several years at Virginia Tech as a research professor before joining NASA. So I'd like to welcome both our speakers, and thank you everyone again for being here.
Aircraft noise research. While we are the two presenters, we're really building on the work of the entire NASA team in acoustics research, aircraft noise. And so much of what you see here is really work that is directly done by NASA researchers in this area. Too numerous to mention them by name, but we wanted to acknowledge them. The topic is aircraft noise research. Next slide, please. And so we start with motivation. Why do we do aircraft noise research? We'll talk about the background, a little bit of background information, talk about the trends in aircraft noise. We'll talk about our near and long-term technology goals. And we'll talk about the strategy we have designed to address these technology goals. We'll talk about an important element of our program, which is partnerships with industry and academia. And then we'll talk about in-house research, which has traditionally been a three-pronged approach to the noise research, comprised of diagnostics, prediction, and noise reduction, often in a synergistic manner. And then we'll close with a summary. Next slide, please. In the way of motivation, as you well know, JPDO is charged with designing the next generation air transportation system, NextGen. And one of its goals is the potential to increase the capacity of air traffic by threefold. Now, clearly, an important enabling technology for that is reducing aircraft noise to enable this growth. Without it, in fact, JPDO studies indicate that the number of people exposed to objectionable noise in and around airports will steadily increase. The graphics is just a visual representation of aerial traffic density. On the left is the current picture, on the right is if we have the 3 times growth. All of these planes in the air must take off from an airport near you and land in an airport near you. So you see that noise is going to be a critical issue. Next slide, please. Before going on, because we'll often be talking about noise levels in dBs, we thought it might be important to discuss what we mean. And because there is some subjectivity in noise, very well-defined metrics have been identified and enforced that define the effect of the noise on the community. They take into account the spectral content, the annoyance rating, duration, and this aggregate metric is called EPNDB, Effective Perceived Noise Level, dB. For the purposes of community noise regulation, there are well-defined so-called certification points that any commercial aircraft flying must meet in order to be certified. And these are so-called approach for landing, takeoff / cutback, and sideline. There are precise trajectories, distances, and durations for these that every aircraft must follow. And the noise is measured, expressed in dB. The chart on the bottom concentrate on the blue bars. Those are really representations of what, say, would be measured at each of the 3 points: approach, cutback, and sideline. In the subsequent charts, we'll often talk about cumulative margins, or margins, more specifically. What we mean by that is for every class of aircraft, there are FAA rules, actually ICAO rules, International Civil Aviation Authority rules, that set limits on the noise that a given aircraft can make. The margins are what the measured level of that particular aircraft is at each cert point, subtracted from the noise regulation level. Generally, you want to be below that, so that's typically a positive number. And then you do that for all 3 certification points. You can express that as a cumulative metric. Often that's what is done. But sometimes for the purposes of identifying trends, you could also look at an average. And both the sum and the average are straightforward arithmetic sums of the dB levels. An important thing to remember about dB is that it's a logarithmic scale, which means if you double the acoustic power, you double the number of engines, the noise will go up by 3 dB. If you want it to go up by 10 dB, you need 10 times the power. So clearly, to make dramatic changes, you need to do a lot, and which the reverse is true also. To reduce significantly the noise, you need to do a lot of work. Next slide, please. This graphic is meant to show where we are today, the general trends, dating back to mid-60s to about mid-2000. Not every aircraft flying is posted there, but a representative set is. And the vertical axis is this average margin relative to stage 3. The stages are the noise regulations, and stage 3 was really the rating rule from the mid-70s to about mid-2000. Clearly, significant progress has been made over the years, and airplanes are much quieter than 20 years ago. But also, it's clear that the trend is leveling off. And why is that? Next slide, please. One main problem is that it is a very complicated problem. Individual sources are highly complicated, involving interactions of flow with every part of the aircraft that makes noise. And then the complicated interactions that the sources could have, the engine slung under the wing, radiating, it's affected, the jet plume is affected by the wing downwash. The noise radiated from the engine scatters off of the fuselage. So it is a complicated problem, And so it's a worthy challenge to rise up to. I think the caption at the bottom really captures it. The aircraft noise is a complex amalgam of sources, integration, interactions, transmission, and propagation. Next slide, please. Against this background of where we are, the challenges we're facing, the Subsonic Fixed Wing Project, part of the 4 fundamental aero programs, has set itself goals to enable the JPDO vision. And there are goals in noise, in emissions, and in performance. And we have identified two generation of aircraft. If today's aircraft are labeled Generation N, then N+1 is the next generation. Still a tube and wing, would look like a, say, 737, but more advanced. And then the follow-up generation, N+2, is something that would probably be radically different. I'm not going to talk about all the goals of the Subsonic Fixed Wing Project. We'll just concentrate on the noise. But the point to make here is that the levels, the targets you see, whether it's for N+1 or N+2, are meant to be the corners of the trade space. If you were to optimize an aircraft just for noise, have acceptable performance elsewhere, but really targeted at noise, those are the targets we think are achievable with the technology that is already in the pipeline and what is over the horizon. These are cumulative margins relative to stage 3. So let's just look at an average, which means for N+1 we're looking at 14 dB and for N+2 17 dB. Next chart, please. They're spotted against the current trends. Clearly a step change in the way we do things. And remember the dB math, that's a significant change. So the goals of the program are very aggressive, but I think that's the kind of thing is needed to achieve the JPDO vision. Next slide, please. A little bit more detail. This is in-house NASA study. The orange bars are margins of a best-in-class, if you will, single-aisle aircraft, something like a 737. In fact, this one is an A320. It shows where it is today relative to stage 3 and on a cumulative basis. The light yellow bars all the way to the right are the ones that is our vision of the replacement for the 737 or A320 that brings the best of the technologies available today or in the pipeline. And you see that it's a significant change. Technologies having to do with the better airframe design, so-called ultra-high bypass ratio cycle engines, and some additional airframe and engine noise reduction technologies. Together, the so-called N+1 achieves the 42 dB goal. In fact, the goal was set on the basis of this study. Next chart, please. Somewhat more nebulous is the N+2 design study. The dark blue, the current state of the art, is a 777, a 600,000-pound aircraft. The light blue in the middle are our vision of a so-called hybrid wing aircraft that would have significant, again, improvements over N+1, cumulatively about 52 dB. We'll talk about the hybrid wing in great detail later, but principally it is the way the propulsion system and airframe are integrated and the significant shielding that you would get from that integration that buys you the benefits. For comparison's sake, we have also spotted the SAX-40. That was the design, the aircraft that was designed based on the University of Cambridge and Massachusetts Institute of Technology's consortium over the course of 3 years, what they called a functionally silent aircraft that it would be blending with the background noise. So it was highly optimized for noise. And there were tremendous technical challenges that had to be overcome. They were way down there at about 86 dB cumulative. They had a much longer time horizon than what we are proposing to do. So we are naturally a little bit more conservative, and hence the goal is at 52. Next slide, please. Our research plan, this is really kind of a common template between all fundamental aero programs, perhaps the entire aeronautics program. It is a layered approach that starts at the basis with the fundamentals, really understanding the physics of the problem and addressing the issues that one has, whether it's prediction, mitigation, or diagnostics for that matter. Then build technologies and tools at the discipline level, in this case acoustics, that address those needs, and then push that up to the next level, integrate with multiple disciplines, and validate primarily the tools that, prediction tools that we are developing, but also technologies, and ultimately lead to a multidisciplinary analysis and optimization. The knowledge and capabilities flow up, the requirements and needs flow down, and ideally this is a continuous loop so things improve constantly. The research effort is too big for just one entity, so what we have here is in-house we do what NASA does best, fundamental, leading edge research, but we also work with our industry and academic partners to bring in the talents and the capabilities that we may not have in-house. So we have NRA-funded research, primarily with universities, but also with some industry. And we also look and have developed and continue to develop partnerships opportunity with industry and other government organizations. And while NASA in-house research is really at all layers, the NRA-funded research tends to be at the fundamental and the discipline level, although it can creep up to the next layer. And the cooperative agreements are primarily at the multidisciplinary and system level approaches. Next slide, please. Okay, we talked about the goals, 42 dB relative to stage 3. Here's the technology path. And basically taking the best airframe design today and saying that which is probably a 777 with the best height lift system, and scale that down to the 737 class, assuming you can maintain the noise benefits of that. Add some technologies, some of which we'll talk about, to further mitigate noise from the high lift system, from the slats, from the flaps, and from the landing gear. Then mate that with a new propulsion cycle. Well, not new, but one that has been waiting in the wings, but I think it finally has its time in the spotlight. That's the ultra high bypass engine. Basically, you slow down the fan tip speed. This way, you reduce fan noise. You also reduce jet exhaust velocities, a notoriously difficult problem to mitigate. So you get significant benefits from the cycle alone. But for insurance purposes, we also add some fan noise reduction technologies, specifically, in this case, soft vane stators and over-the-rotor. We'll talk about the soft vane stators later. Both of those technologies, in fact, have NASA patents pending on them. So this is our technology path for N+1. Next slide, please. We have formed partnerships in the past, and we are continuing to develop partnerships now with industry partners who can help us push the front along on these technologies. Specifically on the propulsion side with the ultra-high bypass, we had studies that we did jointly with Pratt & Whitney. Last November, we tested a scale model cycle of their version of a UHB, which is called the gear turbofan. It was tested at subscale, in fact 22-inch scale in wind tunnel, and basically demonstrated the noise reduction benefits of that cycle. We are planning next September to do the test of the over-the-rotor and the soft vane technologies to buy us the extra margin we want to have with the fan noise reduction. There's potential now to work with Pratt & Whitney, still in negotiations with them, to do some integration studies in the wind tunnel. And also they are planning, they have on schedule, in fact, to do a ground test of the fan system for the gear turbofan and a ground test. So there may be an opportunity for us to work with them and compare the scale model noise data with the full scale to see if that connectivity is there the way we think it is. I'll now hand off to my colleague to walk you through the next few slides. Russ?
Good morning. Next slide, please. We continue talking about our partnerships with the NASA Gulfstream partnership. This partnership is centered on the major airframe noise sources for the landing gear, both the noise and the main gear, and the flap side edge noise sources. You can see in the photograph of the aircraft flying, the flaps deployed. The sharp edges on the side are one of the important airframe noise sources. This is a very exciting partnership. It's got a detailed 5-year plan, already 1 year into the plan. It began in FY07 with a flight test at the Wallops Island Flight Test Facility, and it will continue for the next 4 years, both with additional flight tests, but also a series of component tests of increasing complexity. So in the lower right-hand corner, you see a nose gear being tested in the basic aerodynamic research tunnel, taking detailed flow field measurements. It'll be followed by acoustic measurements, and then progressing on to a full aircraft configuration tested in the 14 by 22 foot wind tunnel of the same G550 aircraft flying. The point of these very well-ordered tests is to come up with a comprehensive benchmark data set for these major airframe noise sources. That will be used for understanding, of course. It will also guide the prediction method development and validation, and of course, be a platform for noise reduction studies. So a very comprehensive long-term partnership here with Gulfstream. Next chart, please. Now we switch gears significantly here to the N+2 generation of aircraft, envisioned to be hybrid wing-body concepts, and only one notional concept here is shown. And compared to the conventional configuration that you've seen pictures of up till now, this represents a paradigm shift in what is possible with aircraft noise. Most dramatically, you see the engines can now be moved from the bottom of the aircraft to the top. And this introduces the potential for shielding of propulsion noise sources. So clearly, with the engines in the location that they're at now in this graphic, you see the potential for large shielding of the forward radiated propulsion noise sources. It'll be a challenge to obtain shielding of the aft radiated sources, and so that is going to be a large focus of continuing work. It also changes the way the aircraft flies and the way the high lift system is integrated into the aircraft because of the blended wing body shape. There's that blending of the airframe components as well. Next chart, please. We've just concluded round 2 of the subsonic fixed wing in-array process, and I'll discuss several of the awards there that are very important in the acoustics area and directly related to this N+2 technology path. The first award that was just completed negotiation and awarded just 3 weeks ago is led by Boeing Phantom Works. They have MIT and University of California, Irvine as subcontractors. And we're beginning to integrate a large team from NASA in both the acoustics disciplines, the aerodynamics disciplines, and the system analysis and design optimization discipline as well. The Boeing team was able to take advantage of that same Cambridge MIT Institute work that was done on the Silent Aircraft Initiative over a period of 3 years. And they'll start with these 2 aircraft concepts that are shown. On the left, you see the SAX-40 design with the higher risk, higher payoff technologies that included embedding the engines in the airframe. On the right, you see a lower risk, but still a dramatic step change in technology and noise reduction potential. It's the podded version of this aircraft. The Boeing team will start with these 2 concepts, and over the first year, they will go into much greater detail of the design of these concepts, closing out the aircraft design in 1 year. They will look at technology suites to add to these aircraft, and by the end of the first year, working together with NASA, they will plan in year 2 and year 3 a large-scale, high-fidelity wind tunnel test. If we go to the next chart, we see an artist rendering of what is envisioned for that phase 2 large-scale, high-fidelity wind tunnel test for both aerodynamic as well as acoustic characteristics of this type of aircraft. We see the 14 by 22 wind tunnel with this concept ready for testing there. We have far-field microphones deploy, the latest phased array technology to image the acoustic sources. This is going to be a big challenge. As we bring the airframe noise sources down and the engine noise sources down, it's going to take a greater resolution of measurement technology to properly characterize these. And so this is envisioned for the phase 2. It'll occur in 2010 if we proceed to that stage. Next chart, please. Along a parallel path, a second team led by California Polytechnic with Georgia Tech as subcontractors are also proceeding on a parallel path. In this case, they're going to be focusing on that metric that was listed in the subsonic fixed-wing goals for field length, going after the cruise-efficient, short takeoff and landing subsonic aircraft concept. And you see, again, a rendering of that type of a concept. They'll look at the technology portfolio, including upper surface blowing, externally blown flaps, circulation control wings that enable this short field takeoff. And again, in year 1, they'll be putting together the tool set to design and optimize this type of configuration. A key is going to be how they integrate the acoustic, predict the acoustic characteristics of these technologies integrated into a complete aircraft concept. And then, like the Boeing-led concept, in year 2 and 3, they'll be putting together plans to do a large-scale, high-fidelity wind tunnel test of this type of a concept. In this case, they're aiming now towards the National Full-Scale Aerodynamic Complex, in fact, at the NASA Ames site. Next chart, please. A different set of concepts were awarded in round 2, whereas the first 2 focused on the complete aircraft concept and technology. These are going to focus more on individual technologies, which we think are very promising and can really change the way aircraft are designed and flown and impact the acoustic characteristics. The first is at University of Florida. It's going to be focusing on circulation control. Of course, this technology can dramatically increase lift coefficient and therefore enable lower speed takeoff and landing, and also increase the separation between the aircraft and the community below, and change the airframe sources as a result of that. In particular, they're going to be looking at pulsed circulation control or unsteady circulation control, which can increase the lift while reducing the mass flow requirement through the circulation control jet. And of course, they're going to be developing a very high quality aerodynamic and acoustic data set, which has not been done yet before. And that's going to be a very important step forward in understanding this technology. The second one will be done by University of Notre Dame, and it's on plasma actuators. You see there in the photograph to the right a cylinder in a wind tunnel, and you see smoke visualizing the flow field, flow from left to right. Now normally, flow over a cylinder, you would see a large separation zone downstream, but with the plasma actuators on, the flow is, you see, smooth over the cylinder, and there's no large separation region. And so plasma actuators hold the promise to provide virtual fairings for airframe noise components like the landing gear and the flap side edges. We think it's, again, a very promising technology which has multiple applications, and we're looking forward to this work as well. One of the keys here is to push the technology of plasma actuators to higher Reynolds number, more realistic applications. Next chart, please. So we're very excited about those NRAs and the potential for what they can do in the N+2 category. But now I'll hand it back to Dr. Envia for our in-house research.
Thank you, Russ. Russ did a pretty good job of covering some of the partnerships we have formed and some of the key NRAs that address the N+2 technology development. Equally important, of course, is what we do in-house. and the kind of work that NASA is uniquely capable and qualified of doing. Our in-house research, as I mentioned earlier, it's a formula that has worked well for us in the previous program, so we decided to stick with it, which is a three-pronged approach to addressing noise research as it relates to aircraft. So the diagnostics, understand what is it that you're trying to model and mitigate, then bring to bear noise prediction capability that might exist or you develop. And so it's a combination of improving existing capabilities, but also developing new ones as need arises. The biggest challenge, of course, within this framework is, the thing that is different in this program is that we are going all the way past the system level just for noise to an integrated approach to designing the entire aircraft system. So we need to interface with the MDAO, multidisciplinary analysis and optimization. So the challenge there is that we have set ourselves is to develop a capability that you can basically dial in the fidelity that you need. If you're studying a specific component and you can afford the computer resources and time, you can study that in a great deal of detail, and we'll show some examples of that. But also you can turn the dial to something that perhaps is not as high fidelity but is efficient, so you can do a system level analysis and you can study a number of systems in reasonable amount of time. Ultimately, of course, the diagnostics and prediction are going to help us devise noise reduction technologies that, again, the idea is for them to have minimum impact on the other performance aspects of the aircraft. We have traditionally worked these in a synergistic manner, so there is a give and take and a continuous improvement loop between these. Next slide, please. I'm going to systematically go through and just show highlights. Just like the entire presentation, this is really only a highlight of what we do, but I think these are what NASA is doing very well. In fact, in some cases, at the leading edge of that work. I'm going to talk about two diagnostic techniques, so-called particle image velocimetry and also acoustic phased arrays, but also talk about a new capability we're developing at NASA to really understand liner physics. Next slide, please. On the PIV, particle image velocimetry and phased arrays, the top graph shows an actual visualization of the turbulence in the jet plume of a coannular jet. This was a scale model test. And basically, by seeding the flow with particles that are small enough that don't affect the flow, but are large enough to reflect laser light, and then by very complicated image processing, you can basically develop a snapshot in time of the intricacies of spatial distribution of a major source of, in this case, jet noise, which is turbulence. And this technique is now pushed into the time domain. There have been recent tests at NASA where you can actually sequence this in time and trace the evolution of turbulence in time, which is equally important in jet noise research. And we have also attempted to do PIV for turbomachinery behind fans to understand the evolution of turbulence from the fan rotor as it impinges on the stator. On the bottom is a graphics of another area that NASA is very good at, phased arrays. And what you see on the bottom left is basically it's a main wing and a flap, and the noise source is the discontinuity between the two, the edges that flow gets into, and you get vortex shedding and noise production. Using conventional methods of so-called beamforming, which is the analysis of the phased array data, which is, after all, an acoustic camera, it is not very clear what the primary source is. But a method developed at NASA called DAMAS, the convolution method, actually filters all the extra noise out, and you can focus on the real source, which is the flap side edges. Next slide, please. On the diagnostics, I'm going to talk about now a set of unique capabilities we're developing at NASA to really understand liner physics. With the move toward larger diameter engines, UHBs, the nacelles need to be shorter because of the weight consideration. That reduces the real estate that you have to apply liner. So understanding the liner physics so you can optimize it, take advantage of the minimized real estate is very important. What we are doing in this program, we are developing two sets of unique capabilities to address grazing flow effect on the liner. By that I mean you can measure the liner in static condition. It will have certain performance, certain impedance characteristics. You put flow over it, things change. And of course, there's flow inside the engine, so it's important to understand the effect of the grazing flow. We're developing a capability, actually two capabilities, that address measuring the performance of a liner subject to grazing flow for realistic flow conditions, realistic frequencies, and essentially realistic scale. One is designed, the so-called grazing flow impedance tube, is a facility that allows you to really, under very controlled environment, look at the performance of the liner, subjected to different boundary layer growth, send waves, acoustic waves from upstream or downstream, and understand what the liner is doing. What it does not afford you, this capability, is to put realistic mode content, the modes inside the engine. These are acoustic components from the sources. For that, we are developing a different capability, curved duct test rig, which allows to go the next step, put more realistic modal structure for the noise. Of course, the conditions are not as controlled as the first facility, but together they provide a powerful capability. Please roll the tape. There's an animation of the two facilities. First, typically where you would put liners are in the inlet or in the exhaust duct and the bypass duct. So the idea here is it's a graphic representation of taking a thin slice of the real liner, not scale it, and then put that in the grazing flow impedance tube for testing purposes. The black knobs upstream are speakers. You can dial in the kind of noise feature that you want, and the wires represent leads to the microphones where you make measurements. You can interchange different pieces to control the boundary layer growth. That's the grazing flow. For the next, the one that takes you the next step up is the so-called curved duct test rig. Basically take the real section of, say, it'll be a full scale for a regional jet. Just unroll it, but maintain in the axial direction the curved nature of the duct. Then you can put the samples of the liner with some foam backing in there and make detailed measurements under realistic flow conditions and realistic frequencies. Both of those conditions, both of these facilities are essentially unique. My understanding is that you have external customers already lining up to make measurements in those. Next slide, please. On the modeling and prediction, I'm going to go again, step through only a handful of areas, but I will sample capabilities that are purely computational, capabilities that are a hybrid between computation and analysis, and capabilities that have to do with basically empiricism. We'll talk about the top two bullets about component prediction, fan and jet, and some airframe noise sources like slat and landing gear. We'll talk about propulsion airframe or acoustics, two kinds of interaction, flow interaction and acoustic surface interaction, scattering. And then we'll close with the real challenge, aircraft noise system prediction. We'll walk you through the current capability, Aircraft Noise Prediction Program, ANOP. You probably have heard that acronym before. And then we'll also introduce the future ANOP 2, a new framework that allows this variable fidelity capability that we talked about earlier. Next slide, please. Here's an example of basically a direct computation of fan noise. For a UHB, an ultra-high bypass cycle, jet noise is almost a non-issue. So the fan noise is dominant source. So understanding fan noise is critical. And here's a calculation that takes into account the real geometry of the rotor, real geometry of the stator, and gives you essentially a field solution. You know noise field everywhere. On the left is the sound field upstream of the stator. That's the brown blade row. In the middle is the pressure distribution, unsteady. On the hub tip and on the blade and downstream is the wave propagating downstream. If this was animated, these patterns would be rotating and corkscrewing forward or aft. These are the so-called modes that we talked about earlier. Next slide, please. Jet noise prediction, because it's a much more difficult problem, directly tied in to turbulence. The methods that use direct calculation like DNS or LES are limited to in Reynolds number and to the, they're not really practical Reynolds number of interest. So really the king of the hill today still continues to be these hybrid methods predicated on the so-called acoustic analogy. You basically do a computation using CFD, like you see on the left, and capture the source of noise, namely turbulence, distribution of turbulence kinetic energy, integral length scales, and what have you, and then use that as input to a very rigorous analytical model of the noise that solves for the noise radiation given these sources. And what you see there on top is the CFD prediction for a turbulence in a jet plume, and the bottom is the data. Obviously improvements need to be made, and they continue to be made. On the right is the prediction. It's a bit difficult to see, but that's the idea, that the predictions are pretty close to the measurement. And the angles are really measured from the axis of the jet. 180 degrees is downstream in the jet plume, 0 degrees is upstream. So you don't really expect to get perhaps very good comparison upstream because there are, shielding from the nozzle and all that we're not modeling here. But downstream, certainly where we think this should work, it does work. Next slide, please. Here's an example of the synergy that I talked about, where the computation and diagnostics really work together. This represents a simulation of the slat noise. That's the forward element of the wing that is deployed when you come into land. There's complicated flow in the cove, in the slat, that is prone to instabilities and vortex shedding. This simulation actually helped us identify these two distinct sources. And by knowing what the source is, then you can design noise reduction technologies that address those specific sources, and they've been very successful. Fortunately, we don't have, there's a very nice animation that shows the so-called slat cove filler that mitigates the slat noise. But here's an example of the synergy that we talked about. Next slide, please. Here's an example of a methodology that is primarily empirical in basis, although unlike the old system where it was just the entire landing gear would be considered one source, we give recognition to the fact that the different elements, that the bigger elements make low-frequency noise, the smaller elements make high-frequency noise. So there are different components built that account for, say, the wheels, the main strut, and the smaller parts of the landing gear. The methodology, the prediction capability is empirical in nature, but the input that drives the empirical coefficients comes from CFD. So this is an example of marrying CFD with empirical method. Next slide. I'll now hand back to my colleague, Dr. Thomas, to cover some exciting features that we're working on.
So you've seen some snapshots of individual components being studied and prediction methods being developed. One that we've worked on now for several years is to start to look at the interactions between components, because as you can see in the photograph, you integrate airframe and propulsion, and that creates complexities and interactions that occur. So this is of a flow interaction type, where you see the exhaust flow being affected by the presence of this pylon structure that connects it to the wing, and then later to the wing downwash and flap downwash. So we started several years ago with this approach of studying this basic jet pylon interaction and developing noise prediction tools for it. To do the statistical type of noise prediction development that Ed referred to, the RANS-based CFD methods, you have to, of course, compute the flow field accurately. And so the first chart there in the circuit is a split screen. And on the left, you show temperature, total temperature being measured in a laboratory experiment without a pylon. So this is just a round jet. And on the right is the best off-the-shelf aerodynamic CFD prediction tools. And you can clearly see the difference between measurement and prediction. All right? So just the flow field prediction is off considerably. So basic turbulence model development is a very tough thing. But the team working on this did a very good engineering type of model improvement to the existing turbulence models. And you can see that in the second of those three charts there. If you take half of that in your mind and compare it to the experiments there in the first chart, you see now a dramatic improvement in the prediction, getting the flow field better. That means you're at least getting the gross mixing parameters much closer to reality. We need much better improvements in the way we can predict the basic turbulence of the flow field before we even go on to the next step of noise prediction. But we continue with the best methods to study the interactions and learn what we can and develop noise reduction items, noise reduction concepts from the understanding the best that we have. So we go on in the third chart there to study the interactions. Now you see the pylon, the presence of the pylon making an even more non-symmetric flow field. And then using the statistical-based prediction method called Jet3D, this code, you see there in the noise source map that is computed from that jet-pylon interaction. And you can see very visually there the computed noise sources are very non-symmetric. That's, again, this basic interaction between the jet and the pylon. And then we complete the circuit by comparing with model scale data, and that comparison looks very good. That whole circuit there is a very fruitful interaction between experiment and prediction capability, but it's also intensive. It takes about 2 years to go through that circuit the first time. Now we move on to making improvements in the noise prediction method so they can handle greater range of directivity, greater range of frequency. We make prediction improvements in the basic flow field measurement as well. And then downstream, we look at making use of unsteady methods to improve certain regions of the flow field. So this is, again, a snapshot of 2 years that we will then build on in the future. Next slide, please. That was one example of a flow interaction. Another type of interaction is acoustic scattering, where propulsion noise, for example, is produced at the source and then it radiates out of the engine and it begins to interact with an airframe, and it can either be reflected or it can be shielded. And so in this image here of a prediction being developed, you see of an N2 plus configuration, you see the propulsion noise sources being simulated on top of the airframe and then interacting with the airframe being shielded by the airframe. This is being done on an NRA, around 1 NRA. It's a fast scattering code that is under development. And the key here is really pushing its usefulness to a broader range of frequencies and really working on increasing the computation time. It's still a very computationally intensive process, and to make it more usable, more realistic, we've got to work on that computational requirement. Next chart, please. You've seen now the components being predicted and some of the interactions being predicted. Now, the real challenge, the next challenge, is to integrate them into a complete aircraft system noise prediction method. ANOP, Aircraft Noise Prediction Program, has been a NASA-developed system noise prediction code over 30 years. And it has been a workhorse, very good at what it does. So I'll say a few words about that and primarily focus on the step change to what we need to go to in the future, all right? And hence the name ANOP 2, where we're going to go in the future. And of course, as we get to this aircraft system noise prediction capability, that's our direct link to MDAO. Next chart, please. So first let's talk about the paradigms here. The ANOP paradigm, which is the current paradigm that we have worked on and developed over, again, 30-year period. Here you see the dominant aircraft configuration for the last several decades. In the ANOP prediction method, aircraft noise sources are modeled from their individual prediction methods, and they are grouped as if they were propagating from a single point on the aircraft. The effects from these interactions, like the engine installation, whether it be reflected or shielded, the flow interactions, are either lumped in the individual prediction methods or they're added on as correction factors. The effects of atmosphere, which can be very significant in terms of how it changes the attenuation and the directivity, are added in simplistic ways. And as a result, it's been built up over the years to do what it's done, which is work on that conventional configuration, but it can't venture too far out of that. Most of the methods that have gone into this to create a fast, efficient system noise prediction method are largely semi-empirical. It means they have theoretical components, they have data correlations, curve fits from experimental data, and this has been an extensive process over years, but it's largely based in that paradigm. Next chart, please. Where we want to go, where we need to go in the future to address the goals of the subsonic fixed-wing program and address more directly unconventional configurations with larger noise reduction potential, we need to add much more realism here. We need to model the component noise sources better with higher fidelity methods. We need to represent them in their true locations and address the installation effects, the interactions directly. And we need to model the atmospheric gradients and wind effects, temperature gradients need to be included as well. That will allow us, and we must, venture outside then of the experience base. Again, the ANOP paradigm was based on the conventional configuration and was developed to be quite good at that configuration. But it's largely for evolutionary changes of that configuration. To break out of that paradigm needs a new aircraft system noise prediction method, ANOP2. Now we'll go into a little more detail in the next chart as to this paradigm shift. In the top half, you see the familiar pyramid. And at the wide base there, you have the foundational physics and modeling that we've given some highlights on when we look at the individual sources. ANOP then resides in the green bar there, the discipline level capability. That's where these components are rolled up together into an aircraft system noise prediction method, which can then feed into the MDAO and the system design goals at the top of the pyramid. The bottom half, though, starts to address the magnitude of this change from ANOP to ANOP2. For system design, MDAO capabilities, you need a wide scope. You need to address a wide range of noise reduction technologies, configurations, operations, etc. So the requirement there is for rapid types of calculations. Okay? You can't run high fidelity CFD codes for weeks and weeks. All right? But if we're going to address these types of requirements, we need the high fidelity codes or the products of those high fidelity codes, which are at the bottom, the research codes. These are of increasing fidelity. And so ANOP2 is going to have the very tough job and challenge of being that middle in transferring that knowledge and that high fidelity prediction capability into a usable tool for system noise design. Next chart elaborates more on the magnitude of this challenge. On the bottom there, the half is that wide base, all right, the foundational capability. These are most, not all, of our high fidelity research codes that have been underdeveloped sometimes for many years by teams of researchers or are new codes that are in the process of being developed. These codes, again, are typically research codes, high fidelity, large computational resources. You see there in the middle, beginning that bridge, the installation effects that are being addressed by sets of codes. In the middle there around the porous boundary, the dashed boundary, is the framework for ANOP2. All of these high-fidelity codes are going to be linked into that ANOP2 framework. They're going to have to be accessible, usable to that ANOP2 framework. ANOP, the old ANOP, still resides within that ANOP2 framework as a low-fidelity component of ANOP2. But the installation effects will be added, the improved propagation tools will have to be added to work in this framework. But it's going to be a real challenge to do this. And again, to provide a usable tool to system design and MDAO requirements and then on up to EDS requirements. So this is going to be a great challenge. Next chart, please. And we want to give a picture of ANOP, the capability of ANOP as it exists today with some of these improvements that have begun to be integrated into ANOP. So we'll watch a simulation here. This is a demonstration of ANOP combined with a propagation tool, one of the propagation tools. It's a simulation of a 777 with a GE90 flying over a terrain. This terrain is from the U.S. Geological Survey. You can download it. ANOP creates the noise hemisphere, and then RNM propagates it to the ground. And so you see the high noise levels in red, the lower noise levels in blue as the aircraft flies along this track, descending into the canyon and then gaining altitude and flying out. The aircraft is just represented by a dot there, just for the purposes of this simulation. So you can see the applicability of this to precision flying, precise studies of noise as aircraft approach or depart from airports or other applications of community noise interest. Next chart, please. Now we move on to the third in the triumvirate of research, the noise reduction technologies. Well, again, we'll highlight a couple of key technologies, by no means all of them. So in the engine area, we'll look at the soft vane stator. Under the category of interactions, propulsion, airframe, aeroacoustic interaction, we'll look at the PAA chevrons. And then in airframe, we'll look at two noise reduction concepts, the continuous mold line and the landing gear fairings. Next chart, please. The soft stator vane addresses that rotor-stator interaction which Ed addressed earlier. It goes on the stator vane in the bypass duct. And you see in the photograph to the left, it has a perforated surface or a soft pressure release surface on the upper surface. They're now looking at the cross-section of the stator vane. Inside the stator vane, there are cavities of varying depth, which give it a frequency dependence. And then the bottom surface, pressure surface, would be solid. This has been developed over a couple of years. It's been tested in the 4-foot low-speed fan facility. And the results, a typical set of results is shown there in the plot, a solid 1 to 2 dB reduction. But what's very promising about this is that while it was designed for tonal reduction, reduction at the source, it also shows broadband noise reduction. And while it was intended to reduce after-radiated sources, it also reduces the sources that are radiated out the inlet, the forward arc. So this is a very promising technology. The next step is to move this to more realistic, higher speed fan applications, and that can be done in the 9x15 test of a UHB concept. Next chart, please. The PA integrated chevrons. This is a large story covering one of our recent partnerships. This started in 2003. It was a partnership between Boeing, NASA, General Electric, Goodrich, and the FAA, who provided critical funding to this whole project. And it again addressed, this part of the partnership addressed this idea of integration effects and how we could take a technology like chevrons that had been underdeveloped for many years and make it better, get more noise reduction out of it by understanding the integration effects between jet and pylon. And so we did a lot of exploration work. We did the best types of prediction methods that we could bring to bear. And you see an example of that, again, studying that asymmetry created by the interaction of the jet and the pylon. We then went to working technically with Boeing. We went to their facility in the low-speed aeroacoustics facility. This is a facility where we can do this type of system testing, where you have the fuselage, the wing, the high-lift system, and the jet exhaust. It's a very promising type of testing approach necessary for this understanding of interaction effects. We studied a range of technologies, including a family of chevron nozzles that we hypothesized would improve their acoustic performance based on a favorable interaction between jet and pylon. And you see flying in 2005, the best of those nozzles, the T-nozzle, where the chevrons closer to the pylon have a stronger effect on the flow field. They create, they're longer, they have more immersion, they create a stronger interaction, and that works favorably with the pylon and clearly superior to the uniform circumferential chevrons. Now you'll see a trend here. You'll see a theme which is very important. In this case, it's not just about the chevrons, but it's about what we gain from the system testing, all right? The subsystem, system level testing, where we're testing complete models, fuselage, wing, flap system, and propulsion source. You'll see that in the inter-arrays that we talked about in the beginning of the presentation, all right? We're headed towards higher fidelity, large-scale integrated testing where we can address the major interactions and the sources and achieve better understanding. And that relates again then to the system level prediction methods, ANOP and ANOP2. This type of trend is going to be very important. It's also very difficult. To do those types of tests is a great challenge, both from a complexity point of view, an instrumentation point of view, and just a test configuration point of view. Next chart, please. Airframe noise reduction, continuous mold line link. Here we see a large-scale test in the 14 by 22 of a more realistic wing. This is a swept wing. It has a slat with a slat cove filler noise reduction concept, and you can see there the flap has been deflected, but it now has the continuous mold line link, eliminating those sharp edges. Now this was a fixed concept. It didn't actually actuate, all right? It was meant to quantify the noise reduction potential of these sources. And on the right, you see the phased array imaging of these sources. In the top, you see the original wing without the noise reduction added, and in the bottom, you see that these concepts have proven their potential at reducing those sources by several decibels. So this is, again, one step further in the process of developing these concepts, developing the understanding, and then moving on to more realistic prediction and noise reduction applications. Next chart, please. Landing gear noise reduction. While one team working with Boeing was working on the chevrons, another part of the NASA team, the airframe noise team, was working with Goodrich and Boeing on the landing gear concepts for this flight test. Again, this occurred in 2005, and it was a set of tests at both subscale as well as this full-scale flight application. We've talked about the landing gear and the complexity of the landing gear, the multiple bluff body shedding sources of the landing gear. This was an attempt at a partial fairing of the landing gear. Again, that balance between application realism and the desire to maybe fair the entire landing gear. And together with the subscale test, it showed good promise. I think what is most important about this is, and this picture really brings it out very clearly, it's again addressing, really motivating us to address these interactions, in this case, between one airframe source, the landing gear, and the other airframe source you see right behind it, the high lift system. The high lift system deployed like this, through the potential flow effect, creates a change in the flow pattern over the landing gear. We have to address that. You can't do that just by a component test of the landing gear. And then the shedding of the vortices and turbulence from the landing gear is in turn impacting the flap source downstream of it. And so this test really brought that out, the motivation to pursue that type of, again, system-level testing, more complex, more ambitious understanding of these interactions. Next chart, please. So we move to summary. We hope we've reminded you that aircraft noise is critical to the future growth of air transport system. People want to move, and they want to move more and more goods and services, and aircraft noise continues to be critical to that growth, enabling that growth. NASA, we continue to work closely with the JPDO, the FAA, to do our part to enable that future growth of the air transport system. We have a very effective three-pronged research approach involving diagnostics, prediction, and noise reduction. And in that three-pronged approach, and then specifically in partnerships, we continue to enjoy and benefit from excellent industry partnerships and engage a number of universities through the NRA process. And finally, the subsonic fixed-wing project has moved out with aggressive noise level targets for both the N1 generation and the N2 generation of aircraft. And then finally, I'd like to say on behalf of the acoustics discipline, my co-speaker here, Dr. Envia, thank you very much for your attention, and we'd be happy to entertain questions.
George Price from the JPDO. Have you rolled up all the things you're doing to see, when you started, you put up some goals. If I remember, it's minus 42 and minus 52, was it, dB? If you take all the things you're doing, have you rolled up projections of that to see how you do against those goals?
I'll answer that question. The goals that were set were based on the internal studies of saying, if you use these technologies, this is what you're going to get. So the goals followed from the study, not the other way around. So the challenge is to demonstrate, to mature those technologies and validate that they would actually achieve those targets.
And if I could add that, I mean, those were based on the studies at the time. We'll continue to improve those studies as we get new information.
Have you looked at the effects of blade mistuning, either natural mistuning or intentional mistuning, to reduce noise?
Of, say, engine sources?
The fan blades or the stator blades?
Well, it will help if that's the primary source. If you can mistune broadband sources, but you can mistune tonal ones. If you do have a dominant tonal noise, that was certainly one approach. Another approach may be active noise control if you're going after just a specific frequency. To answer your question, no, we have not specifically looked at that particular idea. There's a question.
Hi, John Allen from Space Operations. Excellent work, and thank you for sharing that. You mentioned the work that you've done in terms of partnering with industry and with universities. All other federal agencies, obviously, groups like DoD would be interested in the same in similar issues because they have similar concerns.
I can answer that question. We have, the acoustics discipline has these semi-annual technical working group meetings where we invite other government agencies to come and see what we do and provide input. And so they know what our technology portfolio is and if there is an opportunity to work with them. We had the last go around, we had Navy come and present some of their stuff and express the challenges they have for carrier operations with the noise levels and seeing if there was any connectivity, any help that our program can provide to them. So yes, we do have those informally.
Right, Lourdes Maurice from the FAA. I actually have a question, but before I ask my question, I want to go back to the question from the JPDO because I was a little bit confused with the question regarding the noise exposure chart that you showed and the relationship to your aircraft level goals, because I believe that what you showed in noise exposures is looking at the growth in traffic. and the impact and significant exposure to individuals versus your goals are actual technology goals. And I believe that the question was whether we had gone through and taken a look at what would happen to significant exposure, which the JPDO goal is to reduce it in absolute terms, even given growth, if you introduce the technologies in your N+1 or N+2. And I just wanted to note that then certainly the FAA, yourselves, and JPDO did take a look at some of that analysis and did note that indeed, if you were able to achieve those N+1 goals, you could meet the goals of significant reductions, albeit it did take into account a rather aggressive introduction into the fleet, and certainly the caveat is there that it entails a number of assumptions, et cetera. But my question, though, wasn't about that, and it was just taking you back to ANOP, in particular ANOP 2, and the atmospheric effects that you're going to try to build into that. Although it does tie a little bit into the subject of impacts, ultimately we care about noise because of the impacts on the population. My question was whether you thought that through the enhancements in ANOP and then propagating through the entire predictive capability that takes you to exposure, whether you felt that having that capability to take into account atmospheric effects would have an impact in exposure computations.
Well, we feel those propagation effects are important to include. We have evidence that they, temperature gradients, wind effects, can be very significant. And so that's why we think they should be and are working to include those better propagation models. You saw in that box kind of a set of propagation models. The RNM has been linked to ANOP, and we have more advanced methods that are in the stages of being developed and linked.
Did we answer your question?
Hi, this is J.D. Harrington at the podium here. And just a reminder that you participants at the centers can take part in the question and answer session as well. As a matter of fact, I believe we have one from Glenn right now.
Yes, thank you, JD. This is Juan Alonso from NASA headquarters. First of all, my apologies for not being there in person, and thanks for an insightful seminar. I wanted to ask the question that's as follows. As you refine the noise prediction tools, how much or what degree of certainty are we going to be having on the predictions for these N+2 type airplanes? And can you contrast that with the degree of certainty that we have in the predictions for current two-wing airplanes?
I think to specifically address that question, one of the very early milestones we had in the project was to just assess where our tools are today. And we just concluded that exercise. We're going to publish that as a NASA technical publication, where we are actually taking a snapshot today and saying, here's our ability to predict fan noise. Here's the data. Here's the error bar in the data. Here's the error bar sensitivities in the code. So put a marker in the ground saying, this is the delta today. So as we continue to refine, we can always go back and see if you're making actual improvements and making a dent in the data theory discrepancy. So that's an ongoing effort. So we've taken the first step just to establish where we are, and perhaps on an annual basis, maybe for specific components or sources, we can go back and revisit this.
I believe we have one more question from Glenn.
I wonder if you would take a few minutes just to indicate what are the major technical issues that would have to be addressed to achieve the noise goals that you showed early on, that very advanced N+3 configuration. I believe is the MIT Boeing subject.
I heard part of that question. The technical challenges for the N+2 type configuration, I think that's a broad subject. But I'll focus on a couple of comments which I highlighted in the presentation. One is the acoustic scattering. Again, a big paradigm shift to put the engines on top of the aircraft. We've only done some very preliminary experiments of this type of shielding, and so we need better experiments. That's why we're going to that type of large-scale, high-fidelity experiment with good simulation of the propulsion noise sources and the best instrumentation that we can bring to bear to do a good job at that. The prediction method development is going to be a challenge. There are a number of prediction methods that have been out there for a number of years, but they all have severe limitations. So we're focusing on the one that we think has the best opportunity to predict over a wide range of frequencies, and its challenge is going to be the computational resources and doing that in a fast, efficient way. So that's a challenge that we're working on. I think those are two really good challenges.
And let me add that, for a system like a hybrid wing system, the acoustics requirements are not the only ones that are going to drive the design. So part of the challenge would be, dictated by performance, operability, and can you design a fuselage that is not round, a pressure vessel? So there are technical challenges beyond just the acoustics discipline that will drive this.
Well, we had one question that came in that I think might pertain to some people as well. Your seminar primarily seemed to target most of your noise abatement research on the benefit for those on the ground, specifically talking about the aircraft mounted on top of the N+2 aircraft, shielding, I guess, those on the ground. What are you doing about the passengers that are actually flying in the aircraft? Is there any noise research going on for their benefit?
Mm-hmm. We've had a very active core competency in the area of interior noise, transmission through the structure, and mitigation techniques. It's been going on for a number of years. And it was actually part of that QTD2 flight test experiment that we mentioned, two parts of it. That was the third part, was to measure better the interior noise transmission. So yes, that's an important part, especially for N+1, but also for N+2. As we change the configuration, that's going to have impacts on the transmission through the structure. As we push towards lighter weight structures, that's going to impact the interior noise. Lighter weight means less mass damping, and so that's going to have an impact on interior noise. So that remains another key challenge to address.
All right, are there any other questions here at headquarters? All right, I guess with that, we'll close today's seminar. I'd like to thank Dr. Envia and Dr. Thomas for their time in presenting today. If you'd like more information about NASA's aeronautics programs and projects, visit us on the web at www.aeronautics.nasa.gov. Have a great day.